Hello and welcome to this last video on probability that we're going to be doing for this particular topic. We're going to focus on conditional probability. And conditional probability is the one that we use when we are talking about an event that is affected by some additional information that we are told that influences our knowledge on the probability. For example, imagine that we are choosing at random a letter from the word ace. Picture yourself, you have a bag and you have a letter A, C, and E written in independent pieces of paper. The probability of selecting letter A, I put my hand into the bag and I take one letter out. The probability is clearly 1 out of 3 because there's no reason for me to expect that these events are non-equiprobable. So it's 1 out of 3. But what happens if I take my letter out of the bag and then I show it to someone and that someone tells me you took a vowel out? If I'm told that I selected a vowel, then this probability changes because now I know that C is not an option. So my probability of getting an A is now 1 out of 2 because I have been told additional information. This is what conditional probability is about. It's about you having more information and that changing the value of a probability. This that we have here is called the probability of A given B, or A knowing B. So essentially what we're doing is we are measuring the probability of the first event having the knowledge that this actually happened. In this case, A meant selecting the letter A and B meant selecting a vowel. So this is us given that this is like the reading of how this works, and this is strictly linked to independence because we already talked in the previous video on independence about this law, the one for multiplication. But we can also interpret independence through conditionality, because if two events are independent, then their conditionality is not affected. They're not conditional to one another. This means that events A and B are independent if the probability of A given B is the same as the probability of A given not B. This means either B happens or either B doesn't happen, the probability of A remains the same. This is another way of understanding how independence works now through conditionality. So this is something that may also be considered. With that in mind, we can also generalize the multiplication law, and we can find that the probability of the intersection can be found as the probability of A times the probability of B given A. This is the probability of two events occurring at the same time, in this case events that are dependent, has to do with the probability of the first event that I'm looking for, and then the second event in the scenario where the first event actually happens, so that we are still in the intersection, because B could happen outside of A. So what we're looking for is, okay, B happening with the knowledge of A also happening. So from here we get this other very interesting property, this very interesting formula that is usually expressed in this. That this is the formula for how we calculate conditional probability. Note that I have switched around these two, and these two, if you switch around, it's important because this is probability of B knowing A, and now I'm using A knowing B. So just that. And this is like this is the formula that we are using to calculate conditional probability. This is probability of A given B is the probability of the intersection of A and B over the probability of the events that we know of the second event. So with that in mind, we're going to look at this exercise. It's a very interesting exercise that I usually include in my lessons, that I believe that is kind of a very interesting way to close the topic on probability because it makes kind of a lot of things here. So let's begin. We have a boy that walks to school 60% of the time. This means that the probability that the boy is walking here is 0.6. And then he cycles the remaining 40% of the time. Let's say the probability of C is 0.4. Observe that here we only have two options. He either walks or cycles. There's no other option to include. Then we are told that he is late on 2% of the equations that he cycles. And that is the interesting part that we're going to analyze. We have that he is late on 5% on the occasions that he cycles. I was looking at it unless he walks. Sorry, I was reading wrongly. He's late on 5% of the occasions that he walks. So how does this can be interpreted? Well, this means that the probability that he's late, knowing that he walked, is, and watch out here, this is 0.05. If you didn't put the second O there, it would be a 50%, and now this is just 5%. And then he's late on 2% of the occasion that he cycles. Now, yes, here we have the probability that he's late, knowing that he cycled. This is 0.02. So we're just essentially just converting the information that we have into some mathematical elements that we can find. Now, knowing that he's late, given that he's late, this means knowing that he's late, let's find the probability that he cycled that particular day. This means find the probability that he cycled knowing that he's late. So let's think about this. We know that the probability that he cycled and he's late is equal to the probability that he cycled and he's late over the probability that he's late. Okay? So essentially what we need to do is we need to study how can we find the probability that he cycled and he's late and the probability that he's late in general. We need to find like these two probabilities. Let's start with the intersection. We know from the rule that we saw earlier that the probability of the intersection can be expressed as the probability that he cycles times the probability that he cycles, that he's late, knowing that he cycles. Remember that we are using that the late that is here, we are taking given the other events. So from here, we can find the intersection for these dependent events. So we know this, the probability that he cycled, we know it is 0.4, is here. And then the probability that he's late, knowing that he cycled, is here, is 0.02. So here we got 0.008. That is the probability that he cycles and is late. So this is the value that's going to go here, 0.008. And then we need to think of how the probability that is late is going to work. And think about it in this term. I remember that I said earlier that my only two possible scenarios, the only two means that he has are walking and cycling. So him being late is only going to be related to the fact that he walked or the fact that he cycled. This means that the probability that he's late is the probability that he's late and he walked plus the probability that he's late and he cycled. These are the only actual options because there is no other mean for transport that he can consider. He either walked or he cycled. So being late is because he walked or because he cycled. We already know the one for his cycle, we can get it here, and we can do the very same thing, just finding the probability that he's late and walked. That will be 0.6 times 0.05. So this will be here 0.6 times 0.05 plus the value that we have here, this is 0.008. And this, the probability of being late, gives us 0.038. We divide this 0.038 and we get that the probability that he cycled knowing that he was late is 0.211. As I mentioned earlier, it's a very interesting exercise because it combines a lot of thinking and probability. I like to close this video with this one so that you can get like a more general idea. As usual, you can find more exercises in my webpage, that is, you can access through the link in the description. So thank you for watching, and I hope to see you in my next video that is going to be going over permutations and combinations, another very interesting tool that we can use with probability. So thank you for watching.